invitation to talk. I'm very nervous. Let's see if we can get through the hour without incidents. All right, so I'm going to be talking about Landau Ginzburg mirror symmetry and Landau Ginzburg models, and in particular how they relate to other kinds of mirror symmetry, in particular the famous Collab mirror symmetry and also Borcea Voisin mirror symmetry a little bit. Okay, so Witten conjectured that the Landau Ginzburg models were actually different phases, and the sigma models of Collab models were different phases of the same theory. So we had a picture like we have these B model Collab things, and then Landau Ginzburg B models, and they were conjectured, as I said, to be different phases somehow of the same theory. These here also referred to as the large complex structure. Limit point. And the Landau Ginzburg models as, say, the Gapner point. Okay, so this fits into a picture which is now called Berglund-Kravitz mirror symmetry, meaning given a particular polynomial representative of a Collab singularity, we can construct these things, and we know there's Collab mirror symmetry. I'll denote YCY. And there's a Collab A model. This is, I'll call orbifold Gromov-Witten theory, of which much is known, and many people have a lot to say about that. And perhaps by the way you've drawn the picture, you can guess that there's something missing. That is, there should be, and there was conjectured to be by physics predicted, that there would be a Landau Ginzburg mirror symmetry as well, and we were missing an A model until about a decade ago, in 2007. And Jarvis and Rowan, following the ideas of Witten, proposed a mathematical structure that is a cohomological field theory that satisfied the requirements that were needed to fit into this picture. And this equivalence here is called the LGCY correspondence. Okay. Let me think what else I want to say about this. All right, so all of the various kinds of arrows that I've drawn here, dotted, squiggly, solid, are verified to some degree and not verified to some degree. There's lots of open questions in any part of this diagram that you'd like to study. I, in particular, study this part of this diagram. So don't ask me questions about any other part of the diagram. No, you can, but I probably won't know the answers. I should say lots of interesting things are known about the LGCY correspondence. In particular, the state spaces of these things have been verified to be the same by Kyoto and Rowan. And this is particularly interesting for me, and those I work with who study FGRW theory, because it tells us that we may be able to learn interesting things about orbifold Gromov-Witten theory by studying FGRW theory. Okay, so as I said, I'll kind of zoom in on this picture, although this is a little misleading because this makes it seem as though Landau Ginzburg mirror symmetry only exists when you're studying Collab objects, and that's not true. Landau Ginzburg mirror symmetry has actually been verified to work out, meaning the A model and the B model are equivalent, even when you choose singularities which are not Collab. So lots of interesting things in the Landau Ginzburg mirror symmetry picture. So I will talk about the history of this picture, or anyway, this portion of the picture. And I will talk about some things that are mysterious to me. And finally, I'll hopefully get to some new work which was inspired by work by Borcea Voisin. Okay, so that's the plan for what's going to happen. We'll see if it works out that way. All right. yesterday where she said we have to do the terrible definition stuff before we get to any of the fun stuff. So that's what has to happen now. So for a minute, we're going to talk about what inputs, I'm going to call it input data, meaning this picture over here exists for lots of different choices of polynomial representatives and symmetry or befold actions and all that kind of thing. So let's talk about what kinds of singularities, and I really mean polynomial representative of singularities, which is a funny distinction to make, but I'll talk about that in a minute, and what choices of groups we're allowed to pick. Okay, so let's start with W will be a polynomial. So our input data will be a pair of a polynomial and a symmetry group. This polynomial needs to be non-degenerate, meaning it has an isolated singularity at the origin. It needs to be quasi-homogeneous, which of course means there should be a unique set of weights. So let's say this polynomial is in this polynomial ring, then there should be a unique set of weights. Let's say okay, so for each monomial, you should be able to pick weights so that for each monomial, the total weight of the monomial is 1. And we're also going to stick to what we call invertible polynomials, meaning there are the same number of variables as monomials. I'll give you an example of one of these polynomials in just a second. And if you like, you can add the condition that they need to be Collab, which we could interpret as the sum of these weights needs to be 1. If you want it to fit into this Collab-like picture, you need that condition, but it's not actually required for Landau Ginzburg mirror symmetry. So here's our example of a polynomial like this. All right, so how about x squared plus y cubed z plus z to the 4th. This is a non-degenerate, quasi-homogeneous, invertible.
What is G? The group. G.
Oh, I haven't defined G yet. Yeah, I'm starting with the polynomial, then we'll talk about what groups are allowed. The group choice is dependent on which polynomial you pick. Yeah, okay, so the weights vector here will be, as you can pick, I did in fact pick a Collab singularity. Okay, so invertible is a funny word, I think. Maybe you've seen it before. What does it mean for a polynomial to be invertible? As I said, it means that it has the same number of monomials as variables, but in fact it has a more natural meaning than that, meaning if you make a matrix out of the exponent data, that this matrix will be invertible. And it tells us how to find the dual singularity, in fact, because I want to find, if I'm going to plug W and G into my A model, I need to have some dual set of data to put into my B model. And this matrix here gives me a natural way to do that. Let's say that the exponent matrix of the dual singularity will just be the transpose of this matrix. So what this means is the dual polynomial will correspond to the matrix singularity. Notice that it will also be quasi-homogeneous. Its weights are 1/2, 1/3, 1/6, and it's also still Collab. Okay, let's talk about what symmetry groups I'm allowed to pick. Okay, so let's start by talking about what's the maximal group I could pick. Okay, so this Gmax group is the set of all tuples of rational points between 0 and 1. So such that when I rotate each variable, oops, that's supposed to be a Gn, I get back my original polynomial. Q bar is this set of quasi-homogeneous weights of the polynomial. example, Gmax is generated by 1/2 Okay, so you can check and see, for example, if I rotate, if I multiply x by -1 and I plug it into the polynomial, I get back my original polynomial. If I multiply y by e to the 2 pi I divided by 3 and plug it in, I get back my original polynomial. And in fact, I stole these coordinates because they're actually just the columns of the inverse of this matrix. So if I Okay, so the point is I'm allowed to pick not only this group. If I pick this group, then I get what's called the unorbifolded picture of mirror symmetry. But I'm allowed to pick subgroups of this as long as I pick a subgroup which contains the weights vector. So here's my weights vector in my example. Notice that the weights vector will actually always be an element of the maximal symmetry group. And as long as I pick some group between, think of the subgroup lattice, I'm allowed to pick any group between the thing generated by this, which is like the minimal possible group, and this group here, which is like the maximal possible group. Not like, it is the maximal possible group. Okay, so for a particular, I mean already maybe this is interesting because just for a single singularity that you might be interested in, there could be lots of different polynomial representatives of that singularity, and for each different polynomial representative of your singularity, there could be a number of different symmetry groups you might want to pick, and all of which could potentially give you different FJRW theories, except that if you happen to pick a Collab thing, you already sort of know that whatever happens in the FJRW theory should be equivalent to what happens in orbifold Gromov-Witten theory, which means different polynomial representatives of the same singularity should somehow give you the same thing up to isotropy of groups or something. But it's all very, very mysterious how and why this works out, especially if you pick a non-Calabi-Yau singularity. Then we don't even have Gromov-Witten theory as sort of a backbone to understand what's going on. All right, anyway, so moving on. Oh, I never wrote this down. I guess I will. Okay, so I'm almost done just defining the input data. I mean, I did define W and G, the possible polynomials and groups you could pick, but then I've only defined 1/2 of the dual set of data that you would pick once you pick W and G, so I need to now tell you how to find the transpose group, which is sort of fun. So in order to define the transpose group, I need to first define this set. So I'm going to say N is the set of all integer vectors, such that when I just take a simple old dot product, think of my group elements as vectors, that I always get an integer for every group element. So this set N of integer vectors grows if I pick a small g and shrinks if I pick a large g. So then G transpose is made from these integer vectors. Because again, remember I told you that the maximal symmetry group for a polynomial is generated by the columns of the inverse of its exponent matrix. So this is the exponent matrix of the dual polynomial. So these are the linear combinations of the columns that I'm allowed to use to get this symmetry group. So this is like a lattice symmetry subgroup thing going on here. Yeah, okay. I guess I'll point this out as well. So these are the conditions that I said are at play for the A model. So if I have two admissible symmetry groups in the A model, G1 contained in G2, then that means they're duals, as you might guess. We'll have an inverse inclusion, reverse inclusion. And in fact, they'll both be contained, of course, in the maximal symmetry group for that polynomial, and they'll also be contained in the special linear group associated associated to that polynomial, meaning.
So in the definition of the transpose group is n and n? Maybe
Oh yeah, this should be. I should pick a different letter, shouldn't I?
But is m in n?
Yes, thank you. Yeah, sorry. That was kind of a pivotal thing to misrepresent there. Okay, so I just wanted to point out then that for the A model you have these two conditions, as I said before. In the B model you have these two conditions here. Your symmetry groups need to be contained in the special linear group and in the maximal symmetry group, and they have these reverse inclusion things going on. Okay. Yeah, all right. Okay. So now let me get to the history of, now that we have the input data and we have a little bit more idea what's going on here. All right. Okay. So I can construct an A model from W and G, and I construct a B model from the dual set of data that we just described. And we want them to be the same, whatever that means. And there's lots of different ways we can tackle this problem, some of which are already sort of done for us. And that is, these things, you could, if you want a baby problem, you could just think of them as graded vector spaces equipped with a pairing. All right, so the definition of the B model vector space was given by Introligator and Borcea in the 90s. And it's not such a terrible thing. I'll even write it down over here. So you take a direct sum over all of the elements of your group that you're using. Yeah, I guess I'll write it like this. Okay, so what I mean by these subscript h's, which I've mangled a little bit, is that we restrict to only the variables which are fixed by whichever group element we're using. So in the notation we've picked down here, it means only the variables which have zeros in their entries. This is called, this thing in here, you may know it as the Milnor ring or the local algebra, depending on where you've heard of it before. But we only want the G transpose invariant parts of those Milnor rings. Oh, and they also have a volume form attached. In H still. Okay, so this is not such a terrible object. It's sort of a nice combinatorial thing. We at Brigham Young University have a lot of undergraduates interested in doing research, and they are perfectly capable of playing around with these things and writing computer code to try and evaluate which things will be equivalent and which things won't, even before they've had any difficult math classes. So easy problems there, perhaps. Okay. Okay, so I guess I should say more about the B model. So in the case that you do something unorbifolded, and remember before I said that unorbifolded means you pick the maximal symmetry group on the A model, which is the same as picking the minimal symmetry group in the B model. So in the case that you pick the trivial group over here, then it's been known for a while what the B model is all about. I guess I'll write down. Hoffman wrote down some things about how to think about higher structure in the B model. The next most highest structure we're going to talk about is Frobenius algebra structure. You could also think of the B model as a Frobenius manifold. And if you're really brave, you could think about higher genus type problems. Okay, and Saito described the Frobenius manifold structure of the Landau Ginzburg B model, and Giventhal gave a very surprising way to extend that into higher genus potentials, things like this. Okay, so as I said, until 2007, we didn't know what the A model should be, and that was given by Fan, Jarvis, and Rowan. So this is defined, but hard to compute. homofold symmetry group, we don't even have a definition really of what should be happening over there, although there are people working on this problem, making good progress. In the A model, we know exactly what should just happen, except that we can't compute it in most examples. There are some examples where these things have been computed. In particular, the A, D, and E singularities were computed. The A singularities by many people. And then more recently, some unimodal and exceptional singularities and things like that. Okay, Kravitz from the University of Michigan verified the equivalence of the state spaces here between the A and the B model. And in the case that you pick the unorbifolded thing, I should write his name also. He also verified the equivalence of the algebra structures. And then even more recently, in 2015, Lee, Saito, and Shen verified that as long as, again, sticking with the unorbifold case, that the A and the B models are equivalent for almost all choices of singularities. Sully here today, he was here yesterday. I think it's still true that if you pick a chain type polynomial ending into, I'm not sure if we know whether that works, but for all other polynomials it does work. Okay, but as you can see from the diagram, there's still lots of open questions. I will for a minute talk about one result in here. Yeah, okay, we'll call it a star result. Sure, why not? Actually, I guess first I should talk a little bit about what the A model state space is like. This is the B model. Okay, so the A model state space is given by
When you say who, like what was the nature of that statement? What did he show?
this one here you're talking about? Yeah, okay, so let me write down what the state space is and then you'll see what the verification would have to be like. So the state space for the A model is shifted Chen-Rouen cohomology relative Okay, so by WG, I mean, I guess for a group element G, you restrict your polynomial again to only those variables that are fixed by the group element G, and then you take the real part of that polynomial and the inverse image of it, and it's this horrible thing, really. No one likes to think about stuff like this. Well, maybe someone does. So it turns out that actually Wall showed that, we'll just call this thing here star 1, and this thing here called star 2. Star 1 for W and G is isomorphic as a graded vector space to star 2 for W and G. In other words, if you're only interested in these things as vector spaces, you can forget that it's relative cohomology at all and just think of it as these local algebras. And it turns out that the local algebra definition is the same as the Chen-Rouen cohomology. Now it's still interesting that the A model for W and G is the same as the B model for W transpose and G transpose, because what we're saying is if you plug in W and G to something like this, you get the same thing as when you plug in W transpose and G transpose, which is a surprising combinatorial kind of thing to discover. Okay. Now, to make progress in this picture of higher structure of the A and the B models, we need to understand perhaps why it's harder. Okay, so to determine the Frobenius algebra structure, requires the calculation of a whole bunch of structure constants, and these structure constants are called correlators, and in this case we need all genus 0 3-point correlators, which means we have a whole bunch of cohomology classes. That is, if you pick any 3 elements in your state space, you can create a cohomology class out of that, and you need to be able to evaluate the integral over m bar 0, 3 of that cohomology class. And you need to be able to do that for all possible combinations of state space elements, which, as you can guess, is not an easy problem to solve. It turns out that when you pick the maximal symmetry group on the A side, what that means is you're restricting yourself when you calculate this local algebra here, and you take only the G invariant pieces of that. Well, if you pick G to be equal G max, that means you're picking almost no pieces. I mean, you can really only pick very few pieces that have interesting monomials and things like that going on in this space. So it turns out that you end up being left with almost all what are called narrow sectors. So let's just remind ourselves. So elements in an A model, for example, recall that this is a direct sum over group elements of these little sectors. I'm just going to use this notation A sub G to denote this whole thing. And we're going to use notation for a particular element, alpha, will be comprised of a monomial, which comes from the Milnor ring, so we'll call that, say, M, and then the group element whose sector it's in. Okay, so if G fixes no variables, meaning if you view G as a tuple, it has no zeros in it, then we call MG a narrow element. That's probably too small to read, huh? Sorry. See if there's any more big chalk pieces up here. And if G fixes any variables, then that means this element is called broad. Narrow and broad. Okay, so it turns out that evaluating these kinds of integrals here is much easier when you have only narrow elements. So when you pick the maximal symmetry group on the A side, you have almost exclusively narrow elements, sometimes only narrow elements. So you can typically define what all of these integrals are, or at least define when they vanish and when they don't vanish. But in the case that you introduce broad sectors, which corresponds to choosing a non-trivial orbifold group, then things become much, much more difficult. Okay, so to calculate the Frobenius manifold structure, we're required to find all structure constants, which means if we pick any tuple, oh, I shouldn't use n again, how about k? All right, so we need to be able to pick any tuple of insertions, and by that I mean elements of our A model, and create cohomology classes and integrate those cohomology classes over n bar 0k depending on what size of tuple we want. So this gets increasingly hard, and as you can guess, when at the bottom of the chart says higher genus structure, I'm sure you can guess what that requires, right? We need to be able to evaluate all of these integrals of cohomology classes over any genus, any number of insertions. And that is why it gets harder and harder as it goes along. Okay, let's see. So, all right, let's see. Okay. I guess I'll just say a little bit about the earlier question, and that is, what exactly did Kravitz do to verify that when you plug in W and G into something like this, you get the same thing as if you plug in W transpose and G transpose? So as I said, the elements in here look like this on both the A and the B model because they come from a similar construction. So the interesting thing that one of the interesting things that Kravitz did in his PhD thesis is that he constructed something called a mirror map, which we still use in a lot of senses today, and that is he thought of a way to, from the monomial in the A model, create a group element in the B model, and then from the group element in the A model, create a monomial in the B model. And it's a pretty interesting and subtle description. It's not obvious why his description is even completely well defined, although it turns out to be. So I encourage you to read about the mirror map sometime if you have time to do that. It's very interesting. Okay, let's see. Okay, so what about when we orbifold here? Yeah, I guess this is good. Okay, so when you orbifold, that means you pick G not equal to G max on the A model. We only have, to my knowledge, one example of this. Someone in here might know more than me about this. But it is the D4 example. So D4 is we're going to take this polynomial representative of D4. And, okay, so you have the quasi-homogeneous weights for D4 are 1/3 and 1/6, I guess. Yeah. But the maximal symmetry group for D4 is actually given by, oh wait, no, that's not right. Oh, well this is 1/3, isn't it? I'm like, what am I doing wrong here?
And before,
Uh-huh.
before it was supposed to be 1/6.
No, I think it was supposed to be 1/6. What, the other
Very
example?
first example.
Yeah, it was 1/6, I'm pretty sure. Unless I wrote an exponent down
But
there.
what's the classical homogeneous weight of y times z?
Well, it depends on what the weight of y and z are, right? So I think the weight of y had to be 1/3. Yeah. Because it was like y cubed plus y z to the 4th.
Right.
So this had to be 1/3. So
Okay.
yeah. Okay, so anyway, the point is there are two symmetry groups you could choose here. So if you choose this one, you get the unorbifolded case and things work out nicely. If you choose the group generated by this element instead, then your your transpose group, or in other words, the dual group that you would plug into the BMAT model, is not trivial. And when that happens, we don't totally know what to do. As you can see in this picture over here, we don't even have a definition of what the B model should be. Well, I mean, we do here. I should say Kravitz actually wrote down the multiplication here. But for Frobenius manifold and higher genus, we don't even really have a definition. However, in this specific case, we could show that the A model, if you choose this polynomial in this group, was actually isomorphic as a full cohomological field theory to the B model using D4 transpose unorbifolded. In other words, it turns out that the B model could just be considered unorbifolded anyway. And that's okay because, as I mentioned, well, I guess I haven't really talked about it that much yet, and I will talk about it right now. In a lot of cases, when you plug in different choices for polynomials and groups, and you expect to get different things out of these state spaces or cohomological field theories, you don't. They collapse on each other. So the fact that this seemingly orbifold A model you would expect to be isomorphic to an orbifold B model, but it turns out to be isomorphic to an unorbifolded B model is okay. So we're sort of cheating to say that that's an orbifold example. I don't know. I guess it is. But this is an interesting thing to investigate if you're interested in it.
You mean for problem structure, you're just considering the unorbifold
For the B model, yes.
model.
Yes.
It's still the same.
Yes. So I should say, well, anyway, this example exists. You can find it if you want to look for it. Okay, so let me also tell you about another theorem. Okay, so this says for W and G satisfying, first of all, that you can choose to break W up into a decoupled sum of polynomials in such a way that also for all G where AG is a non-empty sector of the state space, G fixes all variables of each of the decoupled polynomials or none of them. So in other words, I'm not saying that every group element has to fix all variables or no variables, but I'm saying there's a way to break your polynomial up into decoupled sums of polynomials such that G fixes all the variables of each individual polynomial or none of the variables of each individual polynomial. And the same condition on the B side. So if those conditions are satisfied, then we have that the A model and B model are isomorphic as orbifold Frobenius algebras. All right, so let me just say a word or two about how this theorem was proved. I'm not going to go into too much detail, but as we know from Kravitz's work here, we know that even in the orbifold case, the vector spaces, the underlying state spaces are isomorphic. So the question is just how do you prove that the 3-point correlators match up between the A and the B models? And it turns out that the trick to this theorem was basically proving that you can evaluate a 3-point correlator I'll simplify it a little. So if you calculate a 3-point correlator in this A model or in this A model, you get the same result as long as the insertions actually exist here. So if you pick 3 insertions in here and they are part of the Gmax A model, you can compute that 3-point correlator here, which is easy to do. So we had to construct some careful embeddings into different A models in order to be able to do this. That makes it look like birational or something. It's not. Maybe I'll erase it because that's confusing. Okay. So let me tell you about some mysteries that I've sort of alluded to but haven't really told you about yet. So let's just think about sort of the easiest baby cases that we could consider that are interesting in this picture. You could, if you've been lost by all the horrible things I've done so far, you could tune back in now, and we're going to talk about things that probably most of you know about. Okay, so if you just consider all 3-variable Collab polynomials. What does that even mean? I mean, of course, polynomial representatives of Collab singularities. There are 13 of them. Okay, and if you consider all possible pairs of one of these polynomials with an admissible symmetry group, there are 45 different pairs. But if you calculate all of the FGRW theories associated with these pairs, you only get 5 distinct things. Which is, I don't know, upsetting to me anyway. Except if you view it in the picture of the Collab big square that I drew at the beginning of the lecture, and if you know things about orbifold Gromov-Witten theory, maybe you would know that there are 4 orbifold Gromov-Witten theory things in this case, and then the unorbifolded case, which is a P1. So there are 5 things geometrically that these algebraic objects should line up with. So I mean, that's good. It means the number 5 is probably right, but it's still upsetting because algebraically it's not clear at all why there should only be 5 distinct objects coming out of this. And it's even more upsetting if we expand the question into non-Collab singularities. We still get a lot of collapsing like this, but we have no geometric intuition for why this happens or when it happens. We do have something called the weights and groups. Oh, I think you can't see down there. I'll write it up here. There's a long-known theorem about these, about the A model specifically. I think a topological proof of this has been known for some time, and Julian Tay provided a proof with representation theory if you want a purely algebraic proof of this, which is kind of fun. So if you have 2 polynomials with the same weights, subgroup of both of their maximal symmetry groups, which contains their weights vector, then the A models should be completely isomorphic as full cohomological field theories. Okay, so we know that if you pick two different polynomials but you use the same group and those two polynomials have the same weights vector, that already you should get isomorphic A models. So that should at least cut down this number here. So if we change this to equivalence classes under the weights and groups theorem, this number becomes 23 instead of 45. Still not 5 though. So still sort of a mystery why this happens. And in fact, if you actually create sort of these, what do I want to say, you pick a weight system and you create a lattice of subgroups between maximal symmetry groups and minimal symmetry groups, and then you encode which of the different choices of groups and polynomials give you which of these 5 different A models. It's sort of disturbing that sometimes there are like, you know, subgroups of other groups that sort of collapse onto each other, but then sometimes there's just other groups that have nothing to do with each other that give you the same symmetry or the same FTRW model. So these are some sort of extending this mystery into higher dimensions and possibly even into what this means in the B model is something I'm really interested in pursuing. So the Landau Ginzburg mirror theorem that I promised at the very beginning of the talk is sort of along these lines. So let's see if we can get there. All right, so now I'm going to switch gears and talk about Borcea Voisin mirror symmetry for just a minute. Okay, so in 1992, Voisin gave a way to construct a Collab threefold from a K3 surface and an elliptic curve with involutions, non-symplectic involutions. We'll call them the involution on S and the involution on E. So use this data to construct a Collab threefold, which we will call V sub S cross E. Okay, and if you consider the fixed locus of the involution on the K3 surface, you get a union of curves. Yeah, and then if you'd let n prime be the sum of the genuses of those curves, then it turns out that the Hodge numbers associated to this Collab threefold can be written down as follows. Okay, so it sort of begs the question, is there a way to exchange n and n prime in a natural way for some other Collab threefold? If so, that would be a good candidate for a mirror pair. And in fact, there is such a way. This is the content of Borcea Voisin mirror symmetry. So then we have a method which is the lattice mirror method for finding, we'll call them S star and E star. All right, so we have this method, which we inherit from Borcea Voisin, for constructing a mirror pair out of an elliptic curve and a K3 surface equipped with a non-symplectic involution. Okay, then more recently, Artabani, Bossar, and Sarti, they, constructed a twist map takes this Collab threefold. I guess I'll write it like this. It's supposed to be cross. Yeah, you could even orbifold here. Yeah. In other words, they take the Collab threefold that you get from Voisin's observations to this orbifold Gromov-Witten theory that appeared in Borgelin-Hubsch-Kravitz mirror symmetry. And in fact showed that, okay, so here's the, these are the mirror pairs constructed by Borcea Voisin. And if you take the Borgelin-Hubsch-Kravitz mirror of this in the way I described at the beginning of the talk, meaning you take these duals of both the polynomials and the groups, that these two things are isomorphic. I think that's right, yeah. So in other words, the Borgelin-Hubsch-Kravitz mirror of this Gromov-Witten theory is isomorphic to the Borcea Voisin mirror of this Collab threefold here, which is surprising and very cool. And in fact, they described how this twist map should work geometrically and in any dimension, subject to some constraints on the weights associated to these polynomials.
What is x here? X transpose is x some polynomial or something?
These transposes here.
Yeah.
So in the case of the polynomial, it's the one where you just transpose their exponent matrix. And in the case of the group, it's where you construct all those integer vectors that give you integer dot products and then use those to construct.
What is x?
Oh, sorry, this is the Collab A model, orbifold Gromov-Witten theory, associated to this singularity and weighted projective space orbifolded by this group. Or perhaps, I think you might need a tilde on that group. It's isotropy of that group. Yes, okay, so let me tell you about this twist map as constructed by Artibani, Voisin, and Sarti. Okay, so this is a map. Consider that you have a polynomial like this. This is our polynomial. This is a polynomial representative of the singularity E, and then this will be a polynomial representative of the singularity S. Now I know that I told you this was an elliptic curve and a K3 surface, but my point is this twist map works for any dimension you want to pick instead of elliptic curves and K3 surfaces. But we do require that these both be Collab, which means the weight system associated with just F and with just G must sum to 1/2. So F and G are called semi-Collab in a subsequent paper by Kyoto, Kalashnikov, and Vignani, where they expanded on these results into higher dimensions and also extended into Landau Ginzburg models instead of only Collab models. But let me continue to describe this twist map. Okay, so we have these things here. These are both, again, we're thinking these as singularities in weighted projective spaces. Let's say this is the weighted projective space of the first polynomial, and this will be the weighted projective space of the second polynomial. Then Artibani, Voisin, and Sarti construct this map that takes the product of these two weighted projective spaces, sends it to this weighted projective space. And I guess I'll spare you the details of this map because I'm running out of time, but I will just say that it requires that the GCD of U naught and V naught equal 1. Okay, so let me tell you a little bit about our theorem in the last 10 minutes that I have. Okay, so
why is it if there's some of the weights plus some of to have their product?
they're not, they're called half Collab. If they sum to 1, then they're Collab.
But you want the whole thing to be a Collab, right?
Yes. So since the weight of x naught is 1/2, that must mean the weight of the sum to 1/2. So we're calling things of that nature semi-Calabi-Yau. They're definitely not Calabi-Yau. And the way this twist map works effectively is that if you restrict this space to the product of the two singularities that we obtain from these two polynomials, the closure of the image of this map is the singularity you obtain from just f minus g. And now this is, again, Calabi-Yau, so it works out nicely. Okay, so let me see. Okay, so let's say that W, so and what follows, this is joint work with Nathan Curtis and Andrew Shaw. Okay, so let's let W be the sum of something that looks like what I've just described. And we'll say the twist of W is f minus g, just like I described over there. And let's pick any group. So in both the results of Artabuonis, Bossor, and Sarti, and Kyoto, Kalishnikov, and Veniani, we're restricted to only using orbifold groups here, which I didn't mention, which are products of symmetry groups of E and S. But of course, there are many more symmetry groups than things that can be described as direct products of groups. So we pick any G that satisfies that, oh, I guess I need to call it Q. That's what I've been calling it. The Q associated to the X variables. And the Q associated to the Y variables need to each be contained in my group, and it just needs to be contained in the special linear groups of WX, WY, meaning those associated to the X variables and the Y variables. Okay, then we have it's going to be a single group element. That is just, I'm using this sort of sloppy notation here to denote the fact that I want it to act on X naught with a weight of 1/2 and Y naught with a weight of 1/2 and to not act at all on any of the other variables. Okay. And then there exists an inclusion map. Let's call this VERPHI. Between the two maximal symmetry groups, the one for the twist of W and the one for W. And the way it works is if alpha represents how this group element acts on the X variables and beta represents how it acts on the Y variables, then we map this into 0 alpha, 0 beta. And this is a group homomorphism, in fact. Okay, so we defined the twist group of G, which actually does correspond with the geometry that was described by the previous authors, but this is an algebraic description of this group, and for more general choices of groups, it is the inverse image of the product of sigma with G under this group homomorphism. Okay, so our theorem, our first result, anyway, is that under the conditions described over there, we have that the A model of W in the group generated by sigma times G is isomorphic as a vector space, a graded vector space with a pairing, that is, with A of twist of W, twist of G. And of course, this same theorem actually works in the B side because the description of the state spaces of the A and the B model are the same. So if it works for the A model or works for the B model, the only things that are different between the A and the B model, which I didn't even mention in this talk, is that they have potentially different gradings, but we didn't get into that. And it turns out to be true in either case here. Okay, so let me draw you a picture of how this could present an interesting theorem in Landau Ginzburg mirror symmetry. All right, so here's my picture down here. So far, this picture is really just about state spaces. But I I will say that we have made some progress along the lines of Frobenius algebras as well. Okay, so if I have the A model associated with W and sigma G, according to this theorem up here, it should be isomorphic to the A model associated to the twist of W and the twist of G. And we know from Kravitz that this should be isomorphic to the B model associated to the twist of W transposed and the twist of G transposed. Now, if you think about how I constructed the twist of a polynomial over there, it should be clear to you, with a little bit of thought, that the transpose of a twist of the polynomial is the same thing as the twist of the transpose of a polynomial. So I'm not going to write that down, but I'll just say it out loud. And it also turns out to be true, but much more difficult to prove, that the transpose of the twist of the group is the same thing as the twist of the transpose of the group. So this is actually exactly the same thing as the twist of W transpose and the twist of G transpose. Yes, that's right. Okay, and then again, using Kravitz's work, this should be the same as, did I get that right? Yes, that's right. This should be the same as the B model of W transpose. Oh, sorry, not using sigma, not using Kravitz, using our theorem up here, which I said was also true for B models. So let's call this theorem 1. So this is theorem 1 here, and this is theorem 1 here, and this is Kravitz here. Kravitz's mirror map. So what this means is that here we have a Landau Ginzburg mirror theorem, which is not expected. Although it looks expected, let's talk about why it isn't the natural thing you would expect. So the natural thing would be but that's not what we have here, right? In fact, since G is contained in sigma G, that means sigma G transpose should be contained in G transpose, which should itself be contained in sigma G transpose. So I have this like double inclusion of groups, and yet when I use this group or I use this group, I get the same Landau Ginzburg theorem, which is really surprising, and it's another example of these times where the groups collapse on each other in ways we can't somehow predict. Now, as I mentioned before in the theorem about orbifolded Frobenius algebras, we do have an isomorphism here of algebras. So we have been able to extend this Landau Ginzburg theorem here to also be a theorem about orbifolded Frobenius algebras as well. And I'll end there.
Any questions? Idea of twist.
I think it's in the, I didn't write it down, but the actual definition of how you take, x naught through xn, y naught through yn into a tuple of points here is like a twisting phenomenon, I guess. I showed you in my notes if you want.
So on the Borcea Voisin mirror symmetry side, it's about homomorphism.
Yes, that's right.
And then your theorem is about FGL.
Yes, it's about the equivalence of the Landau Ginzburg models that are conjectured to be and verified to be equivalent to the Collab models as well, the Borcea theory.
So the twist map, the relation is about homomorphism and FGL.
Yes, that's right. Well, no. The twist map of Artiboni, Bossard, and Sarti is between the Borcea Voisin Collab threefold and the Gromov-Witten theory.
Okay, both sides are.
Yeah, that's right. And then the twist map that we give shows how that map corresponds to a twist map on Landau Ginzburg models.
So you mentioned that the interrogator and Bach's paper on Landau Ginzburg orbifolds doesn't define the ring structure, just the space.
Yes, I think that's true. Now you're making me nervous, but I believe that's true. I think the idea for the algebra structure was outlined by Kaufman and then written down carefully by Kravitz, following his ideas.
Any further questions? So let's thank the speaker again.